let's talk about how to find an explicit formula when you're given a sequence. Remember, a sequence is going to have a group of subscripts. And typically it's going to be a sub 1, a sub 2, a sub 3, a sub 4, up to an ending point, like a sub n. Or if we just have the dot dot dots, it goes on infinitely. We make these subscripts in mathematics usually starting with a 1. But in computer science, you could just as easily start at a sub 0, and that's more common to do because in computer science you start numbering things at 0, and this thing matches up with an array. Let's look at the simplest sequence that we might have. 1, 2, 3, 4, 5. And I want to put dot 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 here so that we show that this goes on. A formula for this is a sub n is just equal to the subscript. Now that is only half of the explicit formula because we really need to say where this begins. We're going to say it begins with 1. And n is going to be an integer. The way I've expressed it here, it shows that this goes on infinitely. But you notice we don't have to start at 1. If I wanted to make things the way they do in computer science, start at 0, then a sub n would be 1 less than this, because we're starting here at 1. Notice if I wrote a sequence that started at 0, 0, 1, 2, 3, 4, 5, and I wanted to write a sub n as my explicit formula, I could make it equal to n provided I started the n's at 0. Notice if I wanted to start the subscripts at 1, we could do the same thing by saying a sub 1 is going to be n minus 1. One of these formulas is just as correct as the other, but one of them tends to be easier to deal with when you're dealing with accounting numbers for mathematical notation. The other one is easier to deal with for computer science. Now, suppose we do a problem like number 10 in your text. In number 10, you have a sequence that goes negative 1, 1, negative 1, 1, negative 1, and I'm going to do this as dot, dot, dot. Okay? Otherwise, we would have to provide a range for the sequence, which we can look at also. Now, here, a pattern to use is to take negative 1 and make our subscript the exponent. And this is going to work if we start at 1. So here you see when n is 1, we have negative 1 to the first. When n is 2, we have negative 1 times negative 1, so it becomes a positive 1. So that's going to work. How could you do this if you were writing a computer program and you wanted to start at n of 0? Well, what we could do is we could change the exponent by adding 1, and that would give us the same pattern. Oh, okay. Notice this exponent here could be n plus 1, or it could be n plus 3, basically anything that turns the exponent into an odd number when this is an even number. Okay? Now, suppose we do this. Suppose we had another sequence that goes 1, negative 1, 1, negative 1, 1, and it goes on. You see, this is very much like this one. It's just we're changing the starting point. If I wanted to do this, I could take negative 1, raise it to the nth power, provided I start where? Think about that for a second. If I make it, since I'm starting at a positive 1, I have to start someplace where I'm going to make this negative 1 squared. It's going to be a positive 1 for the first term. The next term is going to be an odd one. If I wanted to, I could start here. Or I could also, I could have written this as greater than 4 or 0, because anything to the 0th power is 1. This would be the way you'd want to do it then if you're doing it as a computer program. A sub n could also be negative 1 to the n plus 1 if you're starting at 1. Suppose we wanted to combine both of these things, kind of like a problem that you have in number 11. Number 11 has 0, 1, negative 2, 3, negative 4, and then 5. Well, this has elements of both pieces here. So what we could do is we can pick this pattern up here to get our number. A sub n is equal to n, and that will work if we do n is greater than or equal to 0. But now, to change the sign, let's pick something from here and do it with the 0, and do the negative 1 to the n plus 1. That formula should give us this pattern, because if we do 0, well, 0 times this thing's going to be 0. If we put a 1 in here, this will be 1. This one's going to be positive because we have negative 1 squared. How could you rewrite this if you wanted to start at 1? Well, you'd have to start the numbering at n minus 1, and then let your sign change with this. Now let's try a problem that looks a little bit harder. Here we have fractions, but if we're going to do this, what we can do is we can just split it into pieces. Looking at the numerator, you see it just goes up 1, 2, 3, 4, 5. So it's like our very first problem. So we can just say it's going to be n, provided n starts at 1. Now if you look at the denominator, it's going up as 2 squared, 3 squared, 4 squared. So the denominator could be 1 more than the numerator squared. And that will work for a problem like this. You should now try some of those other problems that are listed in the syllabus for the group of problems from 10 to 14 to make sure you can do this type of problem.